only want to install the drivers, you know the other stuff. Alright, so Tony's going to explain to you what he's been working on at home for the last
year.
how long?
3 months.
Tony took what he learned in digital electronics and skipped way to the back of the book that we didn't get to.
It actually seems to be working. That's wonderful.
Tony did something right.
I like how he's labeled it, and I can actually follow it. So anything that runs a process has to have a clock. Anything that runs a process has to be able to accept a 0 and a 1, or 0 and a 1.
All right, so I need everyone to go and raise up hands. How many of you know how a computer works? Okay, kind of. How many of you know what a transistor is? How many of you know how it works?
Is it like a computer?
Okay, there we go. So,
I'm going to erase anything you need to. Shove my chair out of the way if you need to.
okay, well, that's something that I probably can have to do.
You're not going to hurt it.
So computers, they all work from a very simple thing. They work from something that's called a transistor. So you can imagine a transistor like a light switch. That's the best way how to describe it. Because all what it does is it turns on and off. That's it. And the way how it turns on and off is if we go and draw a transistor over here. You would have power that's over here, and then you would send a signal. You would send some sort of voltage to the base over here. And if you have voltage at the base, that's going to allow current to flow through, and that's going to turn on an LED. That's going to send some power through. But if you don't have any voltage, you don't get any current that goes through. So it effectively acts like a switch. The important thing is what you can do from this is you can go and build things called logic gates. And I want to see hands. How many of you know what a logic gate is? All right. Actually, who wants to answer this question? I'm not that confident.
I'm not that, no.
No, you're good.
Brandon, why don't you answer?
I'm not that confident either.
So,
A logic gate's going to make a decision based on what's going into it. So a 1 and a 1, if it's an AND gate, OR gate, or an inverter. An inverter is going to switch it to the opposite of whatever's inputted into it. If it's an OR, they have to be opposite. If it's an AND, they have to be the same.
exactly. All what it is just an input-output machine. You're going to have 2 inputs, and you're going to spit out an output. That's all what it is. And if you arrange transistors in a certain way, you can actually go and make logic gates that do certain things. So, if you look at the circuit over here, what do you think this does? Applying from your knowledge from what a transistor does up here. Because if you remember, if you have a voltage that comes in over here, it allows current to flow through. So what this needs is you have to have 2 inputs that have a voltage in order to produce an output. So we can make something called a truth table. And this is effectively like a table that you would see in algebra when you graph. An XY table, you have a function, it does something. Logic gates are basically the same thing. They're just a little bit different. They only function in 1s and 0s. So if you have a 0, if you have a 0 going into X, and you have a 0 going into Y, you don't have any voltage at the base. So guess what? You don't send any voltage. You get a 0. And if you have a 0 or no voltage in either X or Y, you're not going to send any kind of voltage because you need both of these to be active, which means that you only send voltage when you have both of these on. So you have a truth table, and this is something that you would call an AND gate. Now, you can go and make many more logic gates based upon transistors. That's just a step up. You can think of these like abstraction levels. This transistor is the lowest part, a logic gate is the next step. And you have a lot more logic gates than just that. You have AND gates. Or, if I can write,
It's harder when everybody's watching you.
yes,
It's all right.
not, nor, NAND, XOR. So these are a bunch of letters that I don't know how many, like, if they mean anything to you. But if we go through each one, and you just make functions out of these. A lot of input-output tables.
Why he's doing that? Without this logic, you don't have phones, you don't have computers, you don't have anything digital.
Oh,
This is
definitely.
the basis for all of it. Everything. Obviously gets way more complicated. But who discovered binary code?
That I actually do not know.
That's who everybody should thank for everything digital.
I think Alan Turing figured out a lot of the early computer science. In fact, when I get into how this thing runs programs, a lot of it is based upon Alan Turing's work. But if you go through each of these, you're going to have certain truth tables. And what you can do from this is that you can go and create entire logic operations. You can do math with this. So if we go and do something like an AND gate, combined with an OR gate over here, we can go and figure out what this actually means. If we label this input X, Y, Z, we can do X times Y plus Z is going to be equal to F. This is something that you call Boolean algebra. And I'm not going to get into how this specifically works. The main idea, what I want everyone in this room to know, is that you go from transistors to logic gates, and then you can go from logic gates to math. And this is the important part. Once when we have math, we can start making the computer do interesting things, like addition, subtraction, multiplication. You can start running programs. You can start running all of that. This is incredibly important. So,
Read that line to them though. What's that say?
oh, this?
The way you wrote it, yeah.
That's a good point. So, what this means, you're going to AND together X and Y, and then you're going to OR together Z. Basically, AND gates are like the multiplication of logic gates, and OR gates are like the addition of logic gates. You also have one more gate called XOR gate. And this one is a bit tricky. It functions completely different from the rest. You only get a 1 if one of the inputs is a 1 and the other one is a 0. If they're both 1s or both 0s, you don't send an input. This one over here is actually very important when we get to addition. And if I have time, I'm going to go through how you come up with the circuit for that. But the important thing is, you can go and create math from logic gates. So all the computers come down to the transistor. You go and make logic gates. You can do math. I'm going to go on to a very important part, the clock. This part over here. Now if I slow, or actually I think you should be able to see it flashing if I move it a little bit more.
I think it's flashing so fast that the camera can't pick it up. I think.
Yeah, I get you. So if I go slow it down a little bit,
The rest of the stuff is.
you can see the clock flashing at a certain frequency, and you can see the computer doing the operations from that. So we know two things. One, that the clock controls the speed of the computer. Now, another important thing of the clock is if it can control the speed of the computer, then it makes sure that all of the other modules in the computer is synchronous. They function at the same time. That's something very important that you also have to understand. Without the clock, we don't have a computer. Nothing functions at the same time. Everything will be desynchronous or asynchronous. They just wouldn't work together. So the clock helps control the computer's speed and helps all the modules work together. I'm going to go a little bit into how the clock works. So the main thing about the clock is it takes two components, the resistor and capacitor. And what this allows it to do is it allows it to go and charge and discharge, and allows to change the amount of time, how long that takes, which means that we can go and create a timer from it. So if we take a look at how a capacitor charges, if we go and do a time, if we do voltage over time, a capacitor will charge something like this. And a certain chip called the 555 timer, this keeps an eye on the voltage, and it compares voltage between two different points. And as soon as the capacitor reaches maximum charge, it starts discharging. And as soon as it reaches this threshold right over here, the 555 timer detects that, it compares it between another voltage, and then it starts sending current through. So the capacitor charges again, and then the same thing happens. You can go and measure the period in between this. This takes a certain amount of time. And capacitors, they function with a certain amount of time. So the actual equation for this is going to be so I'm not going to go too much into this, but basically RA and RB are resistors, C is the capacitor. If you increase the resistance, the time is going to go up, so the period becomes longer. If you increase capacitance, the time is going to go up, so the period is going to become longer. What I did is I attached a potentiometer, which means that I can have variable resistance, so I can increase resistance or I can decrease resistance. So as you can guess, that's going to change the speed of the clock. So you can make it go very slow, or I can make it go very fast.
When you overclock, that's the same thing that's going on.
Yes. When you overclock, all what you're doing is changing one of these two values in your computer. Now, keep in mind, my computer, maximum frequency is 300 hertz. In your computers, you have something like 4 billion hertz that is running. So it's a lot faster than my computer. So you can imagine that the values for these must be pretty small in order to make it go that fast. That's something to go and consider. But this is the basics on how the clock function works, or the clock module. The next module that I'm going to talk about is going to be what a register is. And this is another part of the computer. So if you go and take a look over here, register A, register B, and a sum register, what does it look like it's doing? What do you notice? Counting? Okay.
Twos. Every two.
Every three, yeah. But here's something that's happening with these. It's storing the value. Right? Yeah. So if you can imagine, you'd want a computer to store values, because if you cannot store values in a computer, then you don't have a computer really. You cannot make anything work. So this is something that's also very important. You have to go and have a register, but how does one work? Do any of you have an idea on how it can work? Any random idea? Anything?
Hexadecimal?
Hexadecimal? That's actually something that I'm going to get into with RAM and memory. Anything else? Anybody have any ideas?
From binary.
Hmm?
Hex is converted from binary, it's what programs use.
He's asking how it's holding that,
Oh, okay.
how it's registering that voltage and holding it.
Okay.
Doesn't always have to be powered to save it.
It's gotta be power, for sure.
Are the logic gates involved?
There are logic gates involved. There you go. That's the answer that I was looking for. You have logic gates involved. Look at that. So we're gonna use something called a flip-flop, and it's not something that you wear in your shoes. At least I don't think so. So
So then,
if we go, that's not it.
is it sad that I learned that from Minecraft?
No. it's
No, no,
not.
no. That's actually that's
okay.
good. That's good.
You can build these in Minecraft,
Yeah,
Yes.
for sure.
that's mostly how I use it.
Yeah, that's one thing that Minecraft does pretty awesome, actually.
I mean, that's part of the reason why they have education for kids.
That's how they get away with Minecraft camp.
They have working computers.
Oh, yeah.
They take thousands of hours.
Yep. Yep.
Okay, so here's how a computer can store value. We have something called a flip-flop, okay? And something that this does is it's going to store whatever value is in D, and it's going to send it over to Q. The reason why this works the way this does is, let's say that we have D1 and we have load. If we go and create a load and we have a D1, we can go and create a circuit that only loads a certain value when load is on. So if you send load through an inverter, and I think I missed something over here. Yes, I did. If you send load through an inverter and you AND it with D1, that means if there is a value in D1, it's going to send that through and it's going to send it to the OR gate. And if that's the case, it's going to go through, because in OR gate, it can send a value when either it's a 1 or a 0. So as long as this AND gate is a 1, you can send a value to D and you can load it in. Or what you can do is you can go and loop it back around, and you can load it back into the flip-flop. And in this case, it will load a value whenever the clock turns high. So on the rising edge of the clock, if you go and take a look at the clock signal, it's going to produce voltage like this. So as soon as the clock goes high, that's going to send a signal to go and load whatever is on the bus. And if you don't know what a bus is, it's basically just, I'm going to go over that in just a second, but it's going to load whatever information is on this line in D1, and it's going to load that in. The registers that I'm using are 8-bit. So you have 8 of these flip-flops, so you can load in 8 different values of 1s and 0s. So you can have the number represented in all 1s or in all 0s, as long as it's 8 digits long. So. So I have a question. If anyone wants to go and answer this, what does this middle line on the computer do? What do you think?
Which line?
This one right over here.
Are you talking about the yellow wire?
Not the yellow wire, but this string. This long,
like the grid?
these long power strips basically. They don't provide power, so I know I just called them power strips.
So you
but
see how
what do you
most of
think
his
you-
breadboards are running north and south, the ones that are running east and west,
Yes,
right?
just the ones that are running east and west.
The blue wires. What do you think all those are tied together for?
Yes, what's specifically about data? Is to go and transfer data. Because if you have everything connected to a roadway, I'm gonna call this a road. This in computer terms, this is called a bus, but I'm going to call this like a roadway because that's not what it is. You can go and transfer whatever is in, let's say from memory, over onto the bus. And if you have something like 10, 10, 10, you can go and send this information and you can put it into things like the B register, or you can put this in the A register, or you can send stuff from the sum register over back to the A register. It allows information to travel through. That's the importance of the bus. All the modules are connected to a bus. So if you want a computer to work, you have to connect it to a single thing that can just transfer data around. And when you have modules connected to a bus, we call this single line the bus. And we have things like register A, register B, sum. When we have these types of things connected to the bus, we want something to tell it when to output to the bus. Because let's say register A is outputting onto the bus and register B is outputting onto the bus, and B is a 0 and A is a 1. What value is on the bus? You're gonna run into a problem because you have to go and tell which one is outputting so you don't overlap. Because if both are outputting at the same time, it's a bit of a confusion on which values are being outputted when. So what you do is you'll input something called tri-state logic, and it's not that, it's the purpose of it is just really simple. You're going to connect these up to the CPU, and you're going to tell it when to enable. So you have two enables really. You have one for storing data, and then you have one for outputting. So you can either tell the computer to load stuff from the bus into the register, or you can tell it to output. And when it outputs, you have to make sure that nothing else is outputting. So you connect, it wouldn't be in all one wire. What it most likely be is you have different wires controlling which register is outputting when. So you can use these registers to control when they output. That way you don't overlap data. That way they don't conflict with each other, and that way you always have a certain value. All computers have a combination of tri-state logic and registers. Without those, you're not able to transmit data. Without those, you cannot store data. And without the bus, you cannot move data around. The next thing that I want to talk about is addition and how computers add. And do any of you know how adding in binary works? Ronald, do you want to answer? You raise your hand. So
It's like if like they're all one, and then the next one's all one, you just like, you take like the two ones, add them together, and then they become 0. And like you keep doing that down the line, and then like essentially putting one over.
yeah, you'll go and carry it. There you go. That's all it is. It's literally the same as our addition. If you go and do something like 7 plus 5, okay? You're going to get a 2. You're going to have a 1 carried over. This is the tens place, and you're going to have a 12. Binary is the same thing. Obviously in binary, if you have 0 plus 0, you're going to get 0. If you have 1 plus 0, you're going to get a 1. But if you have a 1 plus 1, that is not how you draw it. If you have 1 plus 1, you're going to get a 0. But then you're going to carry the 1 over. That's all what it is. Same thing as regular addition. You're just dealing with 2 possible states instead of 10. Because in regular you have 0 through 9, in binary you only have 0 and 1. The addition works the same. But the crazy thing is that you can build a circuit that does this for you. Because if you remember about Boolean algebra, that's basically just math. And if circuits can do math, they can do addition. So let's go and make a circuit that does addition. So, I'm going to try to make this quick. If you do A plus B, and think of, actually, very important thing, try to think of this as a truth table. If you do A plus B, you're going to have 0 plus 0, 0 plus 1, 1 plus 0, 1 plus 1. And if you think of this as a truth table, you're going to have an output. 0, 0, 0, 1, 0, 1, 1, 0. So we know this is the carry. But I want you to think about this for a second and realize that this is a logic gate. That's the XOR gate. I showed this a bit earlier. And I wouldn't blame you if you don't remember it.
X is for exclusive OR gate.
Yep, X is for exclusive OR gates. So, that's all what this is. We have this part down. We can just go and slap in an OR gate and then boom. Or a XOR gate, and you already have half of it done. Then, and then you just have a carry over here. That can be taken care of. Now, if you have carry plus A plus B, you're going to have a different set of circumstances. You're going to have 1 plus 0 plus 0, 1 plus 0 plus 1. That's not, hold on. 1 plus 1 plus 0, 1 plus 1 plus, plus 1, plus 1. And you're going to have an output again. And this time, if you do it, if you do the math, you're going to have these as an output. And all what this is this is a XOR gate, but it's inverted. So you're going to go and send this XOR gate to an inverter. That's all what you're doing. You're just inverting the signal. And then this part over here, that's an OR gate. Because if you have both zeros as an input, you get a 0. But if it's a 1 or a 0, you're going to go and get a 1. So now we can go and build this entire thing from just logic gates. And if we do that, that's just going to be
You have a question?
Oh, you got a question? Who asked a question?
You got a hand up.
Yes.
Does the clock reset?
Huh?
Yeah, it resets to
Does the clock reset?
What do you mean by reset?
Like the number
The
resets.
0 to 9, how it keeps going.
It goes to like 280 and then it restarts.
256.
Okay, there you go. Okay, I like this. I like this. I like how you notice things. Okay, here we go. So, guess what happens? Yeah. Who said overflow? Who said overflow? There you go. Yes, it overflowed. Because guess what? If you have 8 bits of information, okay, and if any of you want to go and have a calculator out, I'm just trying to find space and where to write this. You're going to have 2 to the 0, plus 2 to the first, plus 2 to the second, plus 2 to the third, plus 2 to the fourth, plus 2 to the fifth, plus 2 to the
If any of
sixth.
you guys wanted to take digital electronics, and this is bothering you, then you didn't want to take digital electronics, because this is it. He's truncating the entire year in an hour, the last 30 minutes. This
So,
is what it is.
this.
The whole class.
If you do the math on this, you know what you're going to get? You're going to get 256. And what is that? That's the total number that of numbers that you can represent. You can represent 0 to 255 using 8 bits of information. So if it goes over that, guess what? You have to go and restart. The computer cannot represent anymore. And this has a bunch of cool consequences. You can go and make the circuit do different things. I'm going to get to that eventually. I want to first finish, well actually I don't think I even have to go and finish this. This is not like the full adder circuit. But the thing is, this is something that I wanted to go and tell you. Like I said, logic gates can do Boolean algebra. And if you go and do the math in binary, you're going to get certain inputs and outputs. All what this is an input-output machine. And all what logic gates are input-output machines. So if you combine a bunch of logic gates together, you're just going to get an even bigger input-output machine. In this case, you're going to get an adder. You're going to be able to add numbers together. So it all comes from the transistor. So logic gates, Boolean algebra, transistors, all that is related to computers. You can go and make it do stuff like this. Now, you remember that I was talking about registers, how that stores data, how you have to go and send it a label. So what happens if you have one register and you have address 000 in binary? So that means if you have a logic gate circuit on where you get all zeros, it's going to activate this register. If you have register 2, and you have everything except this one being the 1, it's going to activate that one. Register 3 would be connected to 0010, so on until you get 1111. And you're going to have register 16. So, what is this? What do you think this is? Anybody have a guess?
Set,
Huh?
like a set, maybe, like a bunch of data sets?
Yes, yes.
Around
Because all these
values.
store 8 bits of information at a certain address. What else?
What we talked about in this class, you have to have an address in order to put it somewhere.
What's that memory? There you go, bingo, that's what it is. This is memory. There you go. This is how memory functions. Remember the registers that I was talking about earlier?
No, it's not running.
So yeah, you remember the registers that I was talking about earlier, how they store values? Well, if you combine an address, you can go and create a logic gate circuit that does this. If you have in all ones, it's going to lead you to a certain register. So you can start storing registers in a singular place. You can start retrieving data from a singular place and start sending it around. This is RAM. And this RAM has 16 bytes. So if you can imagine the RAM that has like 16 gigabytes, you have 16 billion of these little ones and zeros controlling the addresses. In this case, I only have 16, so you don't have to think that big. So there you have it. That's how RAM functions. So the way how the computer is set up, you have the memory address. It's right over here. You can go and see what's happening. If it goes to a certain memory address, it loads the value and it sends it to register A. And if you pay attention, the whatever value is in the sum register, when A and B add together, that gets sent to A. And then A gets put, actually no, I'm sorry. A doesn't get put back into RAM. But what it always does, RAM transfers a 3 over to the B register. But also what RAM can do is it can hold instructions. It can hold the instructions for the computer. Now, this is going to be a lot of fun because I'm about to go and get into how you program this thing. And if you've been looking at the computer, which I'm sure most of you have at least, I don't know if you've read everything, but if you've noticed, there's something called an instruction register. Now, this is different from the other registers. You don't just you store 8 bits, yeah, you do. But it isn't really meant for sending anywhere per se. It's split up into 2 halves. Instruction and program. So if you have something like 0101, 1101, what this does is the instruction. The instruction goes from here over to the microcode EEPROMs. It reads the instruction combined with the step that the computer is on, and then it sends whatever the computer needs to do over here to all the other modules. And I'm going to get to what this is in just a moment. But
Hey,
if,
Tony,
yeah,
I'm not cutting you off. Do you wanna carry this on tomorrow?
what time is it right now?
You got about 8 minutes. I'm
Okay.
I'm not stopping you. I'm just saying when you can find a place comfortable to stop, it's a trick to teach you.
Raise your hands if you want to continue watching this tomorrow. We're going to have a little bit of time. Raise your hands. I want to see how popular this is.
It's early release too.
Okay.
Tomorrow, that's what I'm saying. You'll have a nice little short, well, yeah, about 25, 30 minutes.
Yeah.
Finish it. I'm not telling you to stop. You find a comfortable place to stop, but I don't want you to be going and everybody runs out the door.
Actually, I think
That's what they do.
I found a really good place to stop because this is the transition to how programs execute on the computer. I can go and cover this tomorrow. So there we go. There we go. That's it for today. Now before we all are done for the day, how many of you have questions? What can I answer? If you want to come up and see the computer in person, please come up. You can go and see it's right up here. Just go and don't touch anything. Yes?
For the logic gates, how do you know whether it's not, or whether or not it's a 0 or a 1 on the graph?
On a graph?
Yeah.
It depends on the inputs. You're talking about this, right?
Yeah.
Well, let's say we have an AND gate, and whether or not it's going to be a 0 or a 1. So we have X, Y, and we have F. You just go and take a look at what the logic gate does in this case, and you just have to memorize this. In AND gates, you're going to have zeros until you have both a 1, because you have to have a 0 and a 1, and if it's an OR gate, it's 1 or a 0. I have this memorized. And generally, if you're in visual electronics and you're doing this as a class, you're going to have these memorized as well. But that's all what this is. Logic gates have a predetermined amount.
Any of you guys go to any faucet of engineering, whether it's electrical, mechanical, nuclear, fail, you're gonna have to know this. Even if, even in CS, on the basic part of programming hardware, you'll have to know this. So, good job, Tony.
Thank you. Brandon, I saw that you had your hand raised.
So the only thing that's stopping you from basically cranking it up to higher megahertz is thermal, right?
Cranking it up any higher?
Yeah.
Actually, the limit on my clock speed is the potentiometer. I can crank the potentiometer to 1 ohm, which is as low as it can go, and the clock speed shoots up to 300 hertz. If you wanted to go above that to something crazy, you're going to have to get below 1 ohm of resistance, which is really low. But also, you can go and get like crazy small capacitors to also lower the time. And there's another thing that you can do as well that I don't have access to. Breadboards. These are terrible for sending signals because you're going to have static, you're going to have inductance, you're going to have resistance because these aren't perfect. So if you crank the clock speed like really, really high, to say like maybe even 500 hertz even, you're going to start getting failure in the chips. You're not going to be able to get the clock signal and you're going to start to become asynchronous and then the computer just doesn't work. Because if you remember, I talked about how the clock synchronizes everything.
Right.
So that's the limitation of breadboards. But if I was doing this on a PCB, the printed circuit board, those screen boards, I can go and crank it up like really high. That's the ideal thing for this. If you really wanted to go and build a computer that is 8 bits and works wonderfully all the time, you would do it on a PCB. Any other questions? No? All right. Thank you. Do you need me to unlock the phone?
Nope, it's
All right,
gone.
awesome. Okay. So, does everyone remember where we left off yesterday?
Guys, come up here. Don't hide behind things. Just come up here and listen to the man, please. Come on up, guys. Have a seat.
So, if you remember what I covered yesterday, how computers basically just come from transistors. Transistors just what they do, they're basically just switches. You can go and build logic gates. From logic gates, you can go and build bigger circuits like adders, and then from there, you can go and start building more interesting things like registers, RAM, memory, all that stuff. So it's just layers of abstraction. You go and use one tiny thing, you go and build a more complicated thing, you use that complicated thing to build more complicated things. And another thing that we hit on is that everything in a computer is basically just an input and output machine. You go and take a set of inputs and it gives you an output. So, where I left off yesterday was I was talking about the instruction register. So you all remember that registers, they hold 8 bits, right? So they hold 8 bits of information. Well, the instruction register basically does the same thing. So it does hold 8 bits. It can hold 8 bits total. The only difference is that they're split off 4 and 4. So the first 8 bits would be the instruction. Last 8 bits would be just computer usage. So this can go for the memory address register. I'm just going to abbreviate it as MAR. It can go into the A register. It can go into the program counter. You can send it over to RAM as well if you really wanted to. So that's what this is for, and then this is for the instruction. So if you would imagine, you can have 16 possible sets of instructions. So you can start at 0, 0. You can start at 0. You can go to 1, and that's going to end at 15. So 16 total instructions that you can go and do. And within these instructions, you can go and call these programs, basically. So another word for that can be program. And with programs, you can divide programs up into 5 steps. So one program has 5 steps, and in those 5 steps, they can go and trigger different modules to go and turn on and off. So this over here is actually a few programs that I have in the computer. So LDA is load A, add is add, sub is subtract, STA means store A. So you would store whatever is in A, register A into RAM. This would load whatever is in RAM to register A. Add will just take whatever is in RAM over to register B, and it would add the contents together. And then subtract would do the same thing, except you subtract them. LOI is load A immediately. So what it would do is you would go and have a LDI command over here, and it's going to send whatever value over here straight to the A register. Jump, you would have a jump instruction, and then over here you can have the program that it can go and jump to. You have the output, and then you have halt at the end. There's a couple more commands as well that I'm going to see if I can go and get to. So you have instructions, and then you have certain steps. And if I go and move the computer a little bit over to the right, you see these flashing LEDs down over here. These flashing red LEDs. You also see how it's counting up, right? It's counting up at ones. This is the counter. This keeps track of what step it's on. So you can actually see what step it's on over here. When an LED turns off, that's the step it's on. So it goes from 0 to 5. So that's the counter. The reason why that's important is because you can go and combine the counter with the instruction. And here's the way how you would do that. You would have something that's called ROM. That is read-only memory. So you don't write anything into it, you just read from it. So if you have an address, and I covered this yesterday, how you can have multiple addresses from, you can have addresses like this. They go and start at address 0, go to 15. That's only for 4 bits. If you have 8 bits, it will go from 0 to 255. So at every single address, you're going to have a few ones and zeros that are stored there, and that you can go and retrieve and send it out to the rest of the computer. Now, the way how the ROM works is in this address, you're going to take the counter. So you're going to go and take which LEDs are on over here, which ones and zeros specifically, and you're going to take the instruction from the instruction register. Now, basically, you can go and have it set up something like this. So if these 4 bits over here, this is going to be 4 bits long. So if you can have an instruction like 0, or actually that's not a good one. If we do 1, 0, 0, 0, you can have, actually, yeah, the first one how I wrote it was, I wrote that backwards, I'm sorry. So if you have 0, 0, 0, 1, that would be your instruction. The next 3 bits after that, that's going to be whatever step it's on. So if we have all zeros after this, that's the step. That's step 0. And this is the instruction. So we're telling the computer to perform instruction 1 at step 0. And then step 1, and then we can go and continue on from there, step 2, so on and so forth. And then when you go and retrieve the next instruction, it's going to go through the steps until it resets and retrieves a new instruction. So the way how you would actually program this is with the truth table. So you'll remember the truth tables that I did yesterday with the basic logic gates. You have 2 inputs, and then you have an output. So you would have the inputs, and then you would have an output. You're basically doing the same thing for read-only memory ROM, or in this case, on the EEPROM, those are labeled as the microcode EEPROMs over here. So the truth table for this is really complicated. So I'm going to see if I can try to go through this. If you see the instruction and you see the step, I know this is really small. Maybe I can go and try to zoom in on that. I think that's a little bit better. That's not focusing though. Turn off the lights. Is that better? Can you read that? Okay. So you can see that the instructions are up here, and you can see that the steps are over here. And basically, we have a bunch of instructions up here. I don't think you can read those clearly, but the set of instructions would be halt, so that will just stop the computer. Memory address in, instruction register in, instruction register out. Oh, I'm sorry. I mixed those up. It would be A in, A out, instruction register in, instruction register out. No, I once again confused that. RAM in, RAM out. A in, A out. It's really hard to go and read. Sum out. Subtract. Output enable. Counter enable. Counter out. You would have a jump function, and then you would have flags register in. I'm going to see if I can go and get to that eventually. So I just went over the jump function when I was going through example programs, right? So all what that will do is, if I can just go and move this quickly and go back to the computer. all what the jump instruction does is it would execute a different program. So if you go up here on the program counter, which is up here, it sends whatever is in the program counter over to the memory address register, and it retrieves that program and sends it over to the instruction register, and then it executes that program. So that happens at the beginning of every single program. That's what this does. And if you have a jump function, you can tell it to jump to a specific address in memory, and you can go and tell it to do a different program based upon what address you send it to. So I'm going to see if I can make a little bit more sense, since I'm not sure if you understood that. But before I go and do that, I'll just go over here. You go. Those are the instructions. Not the instructions, but those are the steps that that the computer does when it does certain program or instruction. So all the ones over here, I'm just gonna see if I can highlight them. So this is the fetch cycle. It doesn't matter what instruction you're on, it does this at the beginning of the program. You're going to put whatever instruction into the memory address register. It's going to retrieve that, and it's going to retrieve that program, and then you're going to do ran out instruction register in. So it's going to send whatever is in a counter to the memory address, and then from there it's going to do it's going to send whatever is in RAM at that memory address and send it to the instruction register, and then you can start executing other programs. So the point of all this is you can go and program all of this into RAM. All what this is just bits of information. If you're at address, in this case, we focus on these bits over here, 0010, 010, if you're at that address in RAM, it's going to send signals to the computer to do instruction register out, the memory address in, and all what that tells it to do is send the last 4 bits of the instruction register over to the memory address and retrieve whatever is in that, send it to the B register, and add it to whatever is in the A register. And I'm just going to go and stop momentarily right over here. Does anybody have any questions? Can I clarify a few things, since this is confusing? Yeah?
What does the AI and AO mean?
AI and AO. Right over here, right over here. A register in, A register out.
Okay.
So you'll go and send signals on whether or not you want the A register to output or input. But you get the overall big picture, right? You can go and program RAM, or in this case, ROM, because you're only reading from it. You can go and program it to do certain programs when. And these are the predefined programs. You can go and arrange these in a list, so you can go and do different things. And I'm going to go and write an example quickly on what I mean by that. So, how many of you have taken a programming class or are in programming already? Just raise your hands. Okay, so a good amount of you. I'm going to go and write a quick little program in C that does the Fibonacci sequence. I have that copied in my notebook, and I'm going to those of you in programming might have an idea of what this means, even though it's in C, since it's not too different from Java. And if you want, you can also explain it to other people. So all what this does is actually NPM programming. Do you want to go and explain this? I'm curious.
All you, pal.
Basically what it's doing is you're going to set x is equal to 0, y is equal to 1. And you're going to print x, and then you're going to do x plus y is equal to z. And then you're just going to loop this around. As this loops around, you're going to print numbers from the Fibonacci sequence over here. Now we can actually program this into the computer. And if we separate this as defining x, y, and z, setting x and y, we have a while loop, so we want to go and incorporate that. We want an output. We want addition. And we want to set x and y again. And then we want to go and start at 0 if x is greater than 255, because it only loops around when x is lower than 255. So we can actually program this into the computer. And we can do it like this. So we can do LDI is 0, and then store a 13. So what LDI 0 does is this puts a 0 in the A register. Store a 13. Store 0 in X. This is reversed. I'm going to change this quickly. Actually, no, this is fine. Never mind. So we're going to store a 13, which means we're going to go and store a 0 in X. Then we can go and do an output. So that would output the result, which is going to be 0. And then we can do load A1, and that's going to load 1 into A. So this is just resetting or initializing. You can also call it like that. And yeah, these would be reversed. So you would load a 1 in A register, and then from there you would do a store A to address 14 of RAM. So store A and 14 of RAM. So this just means address. That's something to know. These are just addresses of RAM. So you would just store whatever value in RAM to that specific address. From there, you would go and do another output. So you would output the result of whatever's in the A register again. And then you would go and add 13. So you're going to add whatever's in 13. Basically, this is add 13. You're going to add whatever is in address 13 to A. And then you're going to have something called a jump conditional, or jump carry, my bad. Jump carry. And basically, you know how the computer overflows? When it does, it's going to send a signal that it overflowed. This allows it to go back to 0. So we can go and say jump back to 0. And if it doesn't overflow, it's going to skip past that and keep going. So this is the equivalent of a while loop. And if we go past that, we're going to have another store A. Store A 15. Then you're going to load A from 14. And 15 would be Z. So if you think about it, we go and add X and Y together. This is X plus Y. And then we're just going to say store Z. So it's already defined over here that X plus Y is equal to Z. We're just storing Z. And then we're just gonna go, and load whatever's in address 14, again over to the A register, and then we're gonna go and store it in 13. And what this does, is this, right over here. We're setting X and Y again. We're just moving data around. After that, we're just gonna go and do load A15, and then we're gonna go and do a jump to 4. So we're gonna go and jump over here. This would be where the jump occurs. And the load A15, all what that does is, yeah, you would just go and load you would load whatever is in address 15 over to the A register. So that's how this program would work. You can see how you can go and take a program that's in C and put it over to machine language or machine code. And then, I'm not going to go and write this entire program in ones and zeros. I'm just going to go and write a couple of steps in that, just so you can go and get a familiarity with how it would work and how it relates to those right over there. If our first thing was load 0, so we would have at memory address location 0, we would have the instruction 0101, 0000. So this would be the instruction. Value.
Good afternoon, everyone. All of the buses are on campus. Wednesday is over, and all the buses are on campus. All the students can